In this video, we're going to talk about antiderivatives some more, but with certain functions, so exponentials and trigonometric functions. So we're going to start by reminding ourselves the derivative rules for the exponential functions with a function and their exponent. So if we want to take the derivative of e to the power f of x, remember that it's e to the power f of x, so the exponential always appears, and then we multiply by the derivative of the exponent. Okay, now if you have a different base, so a base other than e, you get the same thing. So it's a to the f of x times f prime of x, but you also have this extra factor of ln a. Okay, so these are going to be important when we try to undo these type of derivatives. So because of this, if I just had the derivative of e to the x, it's just e to the x. So this is another reason why base e is the best base, because the derivative is e to the x, which means that the antiderivative is also e to the x. So you want a function that has derivative e to the x, and you know that it's in fact itself. So its derivative is e to the x, its antiderivative is also e to the x. And then adding any constant you want to that. So what if we tried to determine the derivative of the antiderivative of 2e to the 3t? So we might want to pull the 2 out. So the constant multiple rule says we can pull out that 2. Okay. And then if we think about our derivatives, so probably this e to the 3t has to come from an e to the 3t. So let's just see what would happen if I took the derivative of e to the 3t. So using our rule above, it's going to be e to the 3t, but then I have to times by the derivative of the exponent, which is 3. So I get this extra factor of 3. Just like we had an extra number when we were trying to find the reverse power rule. So what we could do instead is add in, we want a 3 there. I guess I don't need this. We want to put a 3 there. So what we can do is we can take our antiderivative and I can multiply it by 1. Okay, so I'm multiplying it by my fancy one, 3 over 3. Okay, so this is one way that you can compute antiderivatives, is to make them have the derivative of the function you know. So that's what I'm trying to do. Okay, so if I multiply by 3 over 3, what I can do is I can take this top 3 and bring it inside the antiderivative and leave the bottom 3 outside. So that's going to become 2 over 3 antiderivative of 3e to the 3t dt. Okay, so constants can move in and out of the integral sign. And now I know what has derivative 3e to the 3t. It's e to the 3t. So that's going to be 2/3 times e to the 3t plus c. Okay, so this is my antiderivative. In fact, it's my family of antiderivatives. And if you want to check, we can just take the derivative. Okay, that's the nice thing about this chapter. You can always check your work by differentiating. So this is going to be 2/3 times what we just said, so e to the 3t times 3. The 3's cancel out, and I get 2e to the 3t. Okay, this is exactly what I started with. Okay, so that's how I know that I got a right antiderivative. So this strategy will always work as long as your function in the exponent is just a multiple of x, so a linear factor of x. Okay, so just like it did with the power rule, if we want to get rid of a number, we can just multiply by 1 over that number. So the antiderivative of e to the kx dx is going to be 1 over k e to the kx plus c. So we're going to get an extra factor of k when we differentiate this thing, and this 1 over k is going to kill it off so that we only end up with e to the kx. Similarly, we could do this for a different base, except we're going to have an extra factor of ln a, because remember the derivative also has ln a, but ln a is also a constant. Okay, so we're able to get rid of it by dividing it. You can't do this with x's or t's or what. They can't have the variable in them. They have to be constants in order for this to work. So this one's going to be 1 over k times ln a, a to the kt. Oh, and then I've now changed to x, so I should change my variables to x plus c. Okay, so these are how we can compute antiderivatives for these functions. So k has to be a constant, okay, and other than 0, obviously, and a is an allowable base. So it's bigger than 0 and not equal to 1. Okay, now we can also do this as long as we have a linear thing up here, which we do. So if I want the antiderivative of 5, negative 7x plus 1, so we could use this rule, or we can try and just work our way out. So probably this would come from 5 to the negative 7x plus 1, something to do with that exponential because it has that exponential. So if I take the derivative of that, I get 5 to the negative 7x plus 1, and then I get times the ln 5, and then also times the derivative of the exponent, which is negative 7. Okay, so these things we don't want in our antiderivative. So we can divide by them because they're constants. Okay, they're both constants. Or you can just force them to be in there. Either way is fine. So maybe I'll do this one 2 ways. It doesn't take very much space here. So if I force them to be in there, what I'm going to do is multiply my integral by negative 7 ln 5 on the top and the bottom. And I missed the x there. Okay, and then what you can do is grab this top one and bring it inside the integral. Okay, so it's going to be 1 over negative 7 ln 5, and then multiplied by, the antiderivative of negative 7 ln 5, 5 to the negative 7x plus 1 dx. Okay, and now we know exactly what has this as its antiderivative because that whole thing is up here. So this is going to be negative 1 over 7 ln 5 times the antiderivative is 5 to the negative 7x plus 1, and then I add my plus c. Okay, so that would be my family of antiderivatives. Or if you use the rule, okay, we would just know that this is, oh, I don't need that. We can go straight to the answer here. Maybe I'll just write it. Okay, so I want to do 1 over, so k, in fact, maybe I should have said up here. So this, in fact, works for the integral of, let's say, e to the kx plus m dx. Okay, where k and m are constants. Okay, it doesn't actually change. So if you add the plus m there, it doesn't matter, except that you add it in the exponential as well. So this is going to be 1 over k, so negative 7 ln 5 times the exponential. And then add our c. So that's using the rule. Okay, but you can also multiply by this fancy 1 and force the missing piece of your integral or your derivative to be in there, because then you know the antiderivative. So trig functions, we also know a bunch of antiderivatives for. So if you remember your derivatives, then you'll know your antiderivatives. So if I wanted the integral of cos x dx, that means I want the derivative of something to equal cos x. Okay, and we know that the derivative of sine x is in fact cos x. So this is going to be sine x plus c. Okay, now if we want the derivative of something to equal negative sine x, okay, well we know that cos of x has derivative negative sine x. So this one is going to be cos of x plus c. Okay, now another way to write this one, because the negative is in the integral, you could actually just omit the negative. So it's going to be sine x dx. So then I want something to have derivative. So derivative of something I want to be, just sine x. So not negative sine x. So my function is going to be negative cos x, because I want to get rid of that negative. Okay, so that means this is going to be negative cos x plus c. So that's another way to think of this antiderivative. Okay, now we can't find the antiderivative of secant x, but we do know the antiderivative of secant squared x, because remember that the derivative of something actually is secant squared x, and that something is tan x. Okay, so this is going to be tan x plus c. Okay, now here our function in the antiderivative is secant x tan x. So I want something to have derivative secant x tan x. And it turns out that secant x has that derivative. So the antiderivative of secant x times tan x is going to be secant x plus c. Okay, so we get an antiderivative for each of the trig function derivatives. Okay, so negative cosecant squared, this was the derivative, the thing that has that as its derivative is cotan x. Okay, now if you don't want the negative in the integral, then you're going to have it on the other side. So secant squared x dx with no negative, then it's going to be negative cotan x plus c. Okay, these say the same thing. And similarly, the negative cosecant x times cotan x, this is cosecant x. That's its derivative. Okay, or again, you could write this as cosecant x cotan x with a positive, and then it's going to be negative cosecant x. Okay, so like I said before, the more derivatives you know, the more antiderivatives you know, because then you know the antiderivative of the thing that you just differentiated, or the derivative you just got. Okay, so these are some trig ones. Obviously, you can put these together. The trig integrals do get quite challenging, but not so much in our class. But if you go forward, sometimes you have to make substitutions with trig, and that gets a bit... Well, we will do some of that, but not quite to the level I'm just talking about. So that is some antiderivatives for some exponential functions and some trigonometric functions.